Good morning and welcome to the lecture number 12 of the course Water Resource Systems, Modeling Techniques and Analysis. We have been talking about optimization techniques in this part of the course, and specifically during the last few lectures I have been dealing with the linear programming problem, and in the last two lectures we have been talking about the simplex method. And specifically in the previous lecture, we have dealt with the multiple solutions. How do we identify the existence of multiple solutions in a linear programming through when we are solving it through simplex method? If you recall, if there is a non-basic variable in the final tableau which has a coefficient of 0 in the row 0 or in the z row, it indicates that that particular non-basic variable can be brought into the basis without changing the objective function value, and therefore, you can generate one more set of solutions. And as you can recall, if you can generate two sets of solutions, you can generate infinitely many number of solutions by taking the linear combinations of the two solutions. That is, we write x star is equal to alpha x 1 plus 1 minus alpha x 2, where alpha is a constant between 0 and 1, and that is how you generate infinitely many number of solutions. And as I have been telling, the existence of multiple solutions to a optimization problem is always advantageous for the decision maker, because your optimal value of the objective function remains the same across all these solutions, but you have an enormous flexibility to choose one solution from the other, and therefore, you have a handful, in fact, more than a handful of solutions possible, all of which leading to the same objective function value, and therefore, you should be able to identify and generate multiple solutions in the linear programming problems. Then we went on to introduce the artificial variables, the concept of the artificial variables, and then how we handle the artificial variables is what we were just talking about towards the end of the lecture. We introduce the artificial variables essentially to make sure that you have an initial basic feasible solution to start off the computations, to start off the simplex algorithm. As long as you have less than or equal to type of constraints, because our standard form is maximization objective function. For the maximization objective function, if all your constraints are less than or equal to type, corresponding to each of the constraints, you would have added one slack variable, which comes with a positive sign there, that is plus x 3 is less than or equal to etcetera you get, and therefore, when you use the original decision variables as non-basic variables, you would have got an initial basic feasible solution. However, when you have greater than or equal to constraints, as you choose your original decision variables as non-basic variables, you will not get an initial basic feasible solution, because the surplus variable in the case of a greater than or equal to constraint comes with a negative sign there, and therefore, you will not get a initial basic feasible solution. For the express purpose of getting an initial basic feasible solution to start off the computations, we introduce the artificial variables in cases where you have greater than or equal to constraints. Associated with each of the greater than or equal to and the equal to constraints, you introduce one artificial variable each. So, the artificial variables are essentially added to constraints of the type greater than or equal to and equal to constraints. Because these were not existent in the original problem, you would like the artificial variables to assume a value of 0 in the final solution, and therefore, you would penalize the objective function for any non-zero value of the artificial variables, and artificial variables are non-negative. Therefore, the only desirable value for the artificial variables will be 0. So, you would like the artificial variables to assume a value of 0 in the objective function, in the final optimal objective function value, and therefore, you penalize the artificial variables you penalize the objective function such that any non-zero value of the artificial variable will pull down the objective function value to a great extent in the case of a maximization problem. And therefore, there is no incentive, in fact, there is a penalty associated with any non-zero value of artificial variables. This we do by the Big M method, and then the way to use the Big M method, we will continue the discussion that we started in the previous class. You take the Z row and then you take the row in which the artificial variable has been introduced, and then transform the Z row using our way of expressing it in the canonical form as we have discussed earlier. Transform the Z row and then use this transformed Z row in your computations in the simplex table. And this transformation you do one by one associated with each of the rows containing the artificial variables. So, you take the Z row, take one of the rows containing the artificial variables, transform the Z row. On this transformed Z row, you take another row containing another artificial variable and then retransform this again, and so on. So, associated with each of the rows containing artificial variables, you do this transformation one at a time. And finally, when you exhaust all the artificial variables, all the rows containing the artificial variables, that transformed row, that final transformed row is what enters as the Z row in your simplex table. I will demonstrate this with a simple example to make it further clear. Okay, so, let us take this example. Maximize Z is equal to 3 x 1 plus 5 x 2. This is the same problem that we have been solving using the graphical method, and the first problem that we solved using simplex method, and so on, except that we will make a slight change in one of the constraints. X 1 less than or equal to 4, 2 x 2 less than or equal to 12, 3 x 1 plus 2 x 2 is equal to 18. Recall that this constraint we had earlier 3 x 1 plus 2 x 2 less than or equal to 18. So, instead of less than or equal to, I would make it as equal to constraint, equal to 18, and x 1 and x 2 are non-negative. Because this is an equal to constraint, if you put x 1 and x 2 as 0, let us say that you would have put a slack variable here, x 1 plus x 3 is equal to 4, 2 x 2 plus x 4 is equal to 12, and because this is already an equality constraint, you cannot add any slack or surplus variables. Therefore, you will retain 3 x 1 plus 2 x 2 is equal to 18. Because of this equality constraint, if you put x 1 and x 2 is equal to 0, what happens? This becomes infeasible. This constraint cannot be satisfied, and therefore, there is no initial basic feasible solution possible. And therefore, to ensure the initial basic feasible solution, we add a artificial variable here. So, we will write this as 3 x 1 plus 2 x 2 plus a 1 is equal to 18, just to start off the computations. So, this is what we do. Your original constraint, your objective function is 3 x 1 plus 5 x 2. I will write this as 3 x 1 plus 5 x 2 plus 0 x 3 plus 0 x 4 minus m into a 1, where I am adding a artificial variable here 3 x 1 plus 2 x 2 plus a 1 is equal to 18. I am adding a artificial variable here. Now, because we add an artificial variable, we introduce a penalty in the objective function, and this penalty will add as minus m into a 1 for the z expression. So, in the z expression, I will write it as minus m into a 1, where m is a large number, and therefore, any non-zero value of a 1 will pull down the value of z, that is the idea, and x 3 and x 4 here are the slack variables associated with these two constraints. Now, there is one row containing the artificial variable. So, what we will do is we will take the z row, we will express this as a row z minus 3 x 1 minus 5 x 2 plus m a 1, that becomes your 0th row or z row, and take it along with this constraint, this row, and transform the z value z row using our earlier method. So, I will write this as z minus 3 x 1 minus 5 x 2 plus m a 1 is equal to 0. So, this is a constraint that I am rewriting is equal to 0, and the row containing the artificial variable is 3 x 1 plus 2 x 2 plus a 1 is equal to 18. So, we will write this in our canonical form. We will write this as minus 3 x 1 minus 5 x 2 0 x 3 0 x 4 m into a 1 is equal to 0. So, this is a row 0 is what we wrote. Then the row containing artificial variable 3 x 1 plus 2 x 2 plus 0 x 3 plus 0 x 4 plus 1 into a 1, this can be a 1. We will write this as a 1 here, is equal to the right hand side, that is 18 here. Now, we will choose this as the pivotal column and this as a pivotal row and transform the z row. Say for example, I want to transform the right hand side. How do I do? 0 minus m into 18 divided by 1. So, minus 18 m. Let us say I want to transform this, because there is a 0, that remains as 0. This, because there is a 0, that remains 0. Let us say we transform this minus 5 minus 2 m by 1. So, minus 2 m minus 5. Let us say I want to transform this minus 3 minus m into 3 divided by 1, that is r into c by p. R is the element in the row of that particular element, which is m. C is the element in the column of that particular element, which is 3. P is 1, which is the pivotal element. So, this is how you transform the z row minus 3 m minus 3 minus 2 m minus 5 0 0 0 minus 18 m. Now, this is what we use in our simplex algorithm first table. So, the transformed row is what we will use in the first table of the simplex. As I mentioned, if you had more number of constraints of the type greater than or equal to, you would have more number of artificial variables. In such a case, you do this transformation one at a time. That means, we took this row now, you got a transformed row. Then on this transformed row, you take another row containing artificial variables and then redo the transformation and so on. So, until you exhaust all the rows containing artificial variables. And then we use the transformed z row or transformed row 0 in the first simplex table. This is what we will write now. So, this is the transformed z row minus 3 m minus 3 minus 2 m minus 5 0 0 0 minus 18 m. So, this is what we write here minus 3 m minus 3 minus 2 m minus 5 0 0 0 minus 18 m, and all other rows you write as they are. So, this is row 1, row 1 is this x 1 plus x 3 is equal to 4, row 2 is 2 x 2 plus x 4 is equal to 12, row 3 is 3 x 1 plus 2 x 2 is equal to 18, that is plus a 1 is what we will write. So, in the row 1 you have x 1 plus x 3 and 0 a 1 is equal to 4. In row 2 you have 0 x 1, 2 x 2, 0 x 3, x 4, 0 a 1 is equal to 12. And in the last row you have the artificial variable, you will write 3 x 1 plus 2 x 2 plus 0 x 3 plus 0 x 4 plus a 1 is equal to 18. So, this is your first table now. Now, because this is the first time you are coming across this m in the simplex table, I will explain it a bit more in detail. Remember always that m is a very large number, and therefore, when you are comparing m with any other number, the m magnitude of m will be much larger compared to any other values that you have here. So, between minus 3 m and minus 2 m, minus 3 m is a larger negative value. Let us say that this was minus 3 m minus 5, only then you take this as a larger number. Let us say this was minus 3 m minus 3 and this was minus 2 m minus 50,000, let us say. Even then this becomes larger negative value. So, m will override all other dimensions, even if you had minus 2 m minus 5 into 10 to the power 6, let us say. But m is so large compared to 10 to the power 6 that minus 3 m will be still larger negative value compared to minus 2 m minus 5 into 10 to the power 6 or whatever. So, this is what you must keep in mind. The coefficient of m will determine the relative magnitude, because m itself is very large here, and therefore, minus 3 m minus 3 is a larger negative number compared to minus 2 m minus 5, and therefore, this becomes the entering variable, that is x 1 becomes the entering variable. And then you do all your calculations and see that you can calculate your B I by A I j only for these two, which turn out to be 4 and 6, and corresponding to the minimum B I by A I j value, you identify the departing variable. In this case, it becomes x 3, and therefore, x 1 enters in place of x 3. You write it as x 1, x 4 and a 1. That is what you write for the second iteration. So, in the second iteration, your basis will be x 1, x 4 and a 1. Recall what you do then. You have identified the pivotal row. First, you transform the pivotal row by dividing it by pivot. Because in this case pivot is 1, this row remains the same. So, that row remains the same. Then all other elements you transform using our expression. The new number is equal to old number minus the element in the pivotal row corresponding to the element E, element in the pivotal column corresponding to the element E, and divided by the pivot itself. So, that is what you do to transform everything. Let us say that this number we want to transform. So, minus 18 m if you want to transform, how this will get transformed? Minus 18 m minus this number minus 3 m minus 3 into 4 divided by the pivot element. Pivot element is 1. So, this becomes minus 18 m, this will be plus 12 m here. Let me rewrite that. I am showing the transformation. So, this will be minus 18 m, this is into 4. So, this will be minus of minus, that is minus 12 m minus 3. So, this if you write, this will be minus 12 m. So, it will be let me rewrite this. We are doing transformation for this number now. So, this will be minus 18 m minus 4 into minus 3 m minus 3 divided by 1. So, this expression is right. Okay, minus 18 m minus 4 into minus 3 m minus 3. So, that comes out to 12 plus minus 6 m. So, you get minus 6 m here, minus 18 m plus 12 m. So, 6 m minus 12. So, this will be minus 6 m plus 12. Like that, you do all the transformations. Let us say you want to transform this now 0. How do we do? 0 minus 1 into minus 3 m minus 3 divided by 1. You get 3 m plus 3. Let us say you want to transform another number, x 3 is already in the departing variable. So, let us transform x 3. So, 0 minus 1 into minus 3m minus 3 divided by 1, that comes 3m plus 3 and so on. So, you do the transformation using exactly the same procedure that we did, except keeping always in mind that m is a large number, and when you are doing the transformation like this, you just keep it as m, you do not change the number. So, you just keep it as a constant m and then do the transformation. So, this is the transform table now. Now, you ask the question whether this is a optimal solution. It is not an optimal solution because there is a negative coefficient here in the z row. Remember here, if you had let us say minus 2m plus 50,000, even then it becomes a negative number because m is very large. So, minus 2m minus 5 is a negative number here, and therefore, this solution is not optimal, and because there is only one negative number, that variable, the variable corresponding to that negative number will enter the basis. So, this is the entering variable. Once you identify the entering variable, calculate bi by aij if it is non-zero, non-negative, and then you will choose that particular variable which has a minimum bi by aij among all these variables for which you could calculate, and that goes out of the basis as a departing variable. So, it makes way for the entering variable x 2. So, you will have your next basis as x 1, x 4 and x 2, and then you do the transformation again of the pivotal row and so on. So, you get to the next iteration. So, x 1, x 4, x 2 is your new basis. Again do the calculation, you will see that there is still one more negative variable minus 9 by 2, and therefore, this becomes the entering variable, and then x 4 becomes the departing variable. Your basis then becomes x 1, x 3 and x 2 in the next row. You in next calculation again redo the calculations, redo the transformation and so on, and go to the next table. When you go to the iteration number 4, when you ask the question, is this solution optimal, and examine the coefficients in the z row of all the variables including the artificial variable, you will see that all these coefficients are non-negative, and therefore, the solution cannot be further improved, and therefore, this becomes the optimal solution. What is the optimal solution? The solution is read as z is equal to 36, x 1 is equal to 2, x 3 is equal to 2, x 2 is equal to 6. So, this is the solution. Now, there are some important aspects that you must remember. You introduce the artificial variable a 1, which was not existent in the problem, much like you introduced x 3 and x 4. For example, these were slack variables. X 3 and x 4 can take non-zero values in the final solution, because essentially you introduce the slack variables to make the constraint as equality constraint. Therefore, x 3 can be non-zero in the final solution. However, a 1 has to be 0 in the final solution, because you have introduced a penalty corresponding to a 1. If there is any a 1 which is non-zero in the optimal solution, if there is any artificial variable which is non-zero in the final solution, it means that the penalty has penalty comes into play in the optimal z value. We will see the implication of that when we proceed further. If there is an artificial variable which has a non-zero value when the optimality criteria is satisfied, let us see what it means presently. So, the solution here is z is equal to 36, x 1 is equal to 2, x 3 is equal to 2 and x 2 is equal to 6. Recall this, when we solved this problem earlier with a less than or equal to constraint, 3 x 1 plus 2 x 2 was less than or equal to 18 in the earlier problem that we solved, and that thing we made it equal to just to demonstrate the artificial variable. When we made this equal to, you still get the same solution, namely x 1 is equal to 2 and x 2 is equal to 6. If you forget about other variables, x 1 is equal to 2 and x 2 is equal to 6 and z is equal to 36 was in fact the solution that you had obtained earlier. Which means what? If you look at this constraint 3 x 1 plus 2 x 2 less than or equal to 18 and you put x 1 is equal to 2 here and x 2 is equal to 6 here, the left hand side becomes equal to 18. Such constraints which are stretched to the full extent, you were saying 3x1 plus 2x2 must be less than or equal to 18, but in the optimal solution it becomes equal to 18. Such constraints are called as the binding constraints or tight constraints. There is no slack available at all. It is a tight constraint. In the optimal solution, it has been completely stretched to its limit. Such constraints are called as tight constraints. In fact, these are important. It is important to identify which are the tight constraints, which are the slack constraints, etc., when you will do the sensitivity analysis, which we will see later on to some extent. Look at the other constraint which you had, x1 is less than or equal to 4. In the optimal solution, you got x1 is equal to 2, which means there is still some slack available there. So, x1 less than or equal to 4 was your original constraint. In the optimal solution, you got x1 is equal to 2. So, there is still a slack of 2 that is available, x3 is equal to 2, because x1 plus x3 you made it as equal to 4 in that particular case, and therefore, the slack variable which is non-zero in this particular case has taken a value of 2. So, that slackness is still available to be satisfied in that particular constraint. That is how you should look at, and in fact, when we do some applications etc., hopefully, we will cover this aspect in slightly more detail. But right now, you just keep in mind that the constraints which are stretched to the full extent in the final optimal solution are called as the tight constraints or binding constraints, and there will be some binding constraints, there will be some slack constraints. The constraints which were not completely stretched in the optimal solution are called as a slack or loose constraints. So, there will be typically there will be some binding constraints, there will be some loose constraints and so on. All right. Now, what we saw was that multiple solutions exist and we know how to capture the multiple solutions, and we introduce the artificial variables to account for greater than or equal to and equal to constraints, just to make sure that you have an initial basic feasible solution to start off the computations. In the graphical method, I introduced several other special cases. For example, you may have an unbounded solution, where the feasible region is unbounded in the direction in which the z is increasing for a maximization problem, and therefore, z can be increased up to infinity without violating any of the constraints, and such problems lead to unbounded solutions. And there may be also infeasible solutions, where the set of constraints is such that there is no intersecting region that these constraints define in the feasible region, and therefore, you cannot find an intersecting feasible region for the type of set for the set of constraints that you have in the original problem. Identification of unbounded solution as well as infeasible solutions is as important as identifying multiple solutions. In fact, both unbounded solutions and the infeasible solutions always indicate that the problem is not correctly formulated. There may be certain constraints that have not been correctly put and so on. So, the moment you come across unbounded solution or the infeasible solution, you should look at your problem formulation, whether the physical features of the problems have been correctly translated into mathematical expressions in terms of the constraints and so on. So, typically if you have an unbounded solution or the infeasible solution, it always indicates that the problem is ill formulated. How do we find an unbounded solution? If you recall, your entering variable you identified based on the highest negative coefficient in the z row. This indicates that the rate of increase in the objective function is much higher if you bring in this particular variable into the basis compared to bringing in any other currently non-basic variables. That is how you identified the entering variable. Then you go to the departing variable. How did you identify the departing variable? It is that particular value, that particular variable which reaches 0 first as you start increasing the value of this freshly entering variable. So, as you start increasing this variable, the one of the non-basic variables will attain one of the currently basic variables will attain 0 first, and that becomes your departing variable. Let us say that a situation exists where you keep on increasing the currently entering variable without making any of these currently basic variables to 0. That means, you keep on increasing the currently entering basic variable without making any of the basic variables to reach 0. That means what? You can increase this particular variable which has been identified as the entering variable up to infinity, and in a maximization problem that leads to the objective function going to infinity. So, if at any iteration you come across a situation where you have been able to identify an entering variable, but you cannot identify any exiting variable, any departing variable, that indicates that the objective function value can be increased ad infinitum up to infinity without violating any of the conditions. That means that the solution is unbounded. So, the unbounded solution is obtained or identified the moment you come across a situation where you are able to identify an entering variable, and therefore, the solution is not optimal. It is saying that the solution can be further improved. However, you are unable to identify any departing variable. Let us look at an example. So, this unbounded solution is a situation where no departing variable can be found at some iteration. You have not reached the optimal solution yet. So, at any intermediate iteration, you come across a situation where departing variable cannot be found. Such a situation leads to an unbounded solution. Let us look at this example. Z is equal to x1 plus x2. We will write x1 greater than or equal to 5 and x2 less than or equal to 10. Just looking at the problem, you know that it is an unbounded solution, because this constraint says that x1 is greater than or equal to 5 and there is no other constraint which will restrict the variable x1. You can keep on increasing x1, and you would like to do that because the objective function is such that as you increase x1, your z will keep on increasing, and you are looking at a maximization problem. Therefore, you would like to increase x1 as much as possible, and you start increasing from 5. There is no restriction, there is no upper bound on x1. So, you keep on increasing x1 up to infinity without violation of any constraint, and therefore, this is obviously an unbounded problem. Let us see what happens if we solve such a problem in using simplex algorithm. So, this we know that it is an unbounded problem. Let us solve this problem with the simplex algorithm and see what happens for such problems. So, this is if you solve it by a graphical method, not solve, just try depict it by graphical method. You have this x1 is less than or equal to 10. So, this is bounded here, but this says x1 is greater than or equal to 5. So, this region to the right of this line x1 is equal to 5 is all feasible, and x2 is less than or equal to 10. So, region lower than this particular line is all feasible. So, the feasible region here is as shown. So, all of this, let us say you extend this. So, all of this region is feasible, and z is increasing in this direction. So, as you increase z, it is moving like this. So, it moves like this in that particular direction. So, it is moving in this direction. So, there is no restriction at all. You keep on moving, still there will be at least one point, and it keeps increasing in this particular direction as x1 increases. So, you can keep on increasing x1 without violating any conditions, and therefore, x1 can go up to infinity and z will reach infinity at that particular point, and therefore, this is a unbounded solution. Let us solve this using a simplex method. X1 is greater than or equal to 5, I will write it as x1 minus x3 is equal to 5. This is a surplus variable because it is a greater than or equal to constraint, and then x2 is less than or equal to 10, I will write it as x2 plus x4 is equal to 10. This is a slack variable, and your objective function is z is equal to x1 plus x2, all these are non-negative variables. Because you have a minus x3 is here, that means because you have a greater than or equal to constraint, you add an artificial variable here. So, we will add an artificial variable and write this constraint as x1 minus x3 plus a1 is equal to 5. So, this is the artificial variable that we have added. Because you added artificial variable, you penalize the objective function. So, you would have written z is equal to x1 plus x2 plus 0 x3 plus 0 x4 minus m into a1, because you are penalizing the objective function, and therefore, when you write the z row, it becomes plus m a1. So, z row is written as z minus x1 minus x2 plus m a1 is equal to 0. Now, you take all these variables. So, you are first transforming the coefficients of z row. So, this is a z row, this is a row containing the artificial variable. You do all this transformation like we did in the previous example and rewrite the transformed row. So, this is the transformed row minus 1 minus m minus 1 m 0 0 minus m minus 5 m. So, this becomes the transformed z row. This is what we use in the first simplex tableau. So, we write the simplex tableau row 0 1 2. Now, this is row 0 minus 1 minus m minus 1 m 0 0 minus 5 m. So, this is minus 1 minus m minus 1 m 0 0 minus 5 m, and row 1 is your x1 minus x3 plus a1. This is a row 1. So, x1 plus 0 x2 minus x3 0 x4 plus a1 is equal to 5. Like this you write row 1 and row 2. So, you identify the entering variable. This is the entering variable minus 1 minus m, because this is the highest negative value, and this becomes entering and this becomes departing, because bi by aij is minimal among all the values that you could calculate. In fact, this is the only value, and therefore, this becomes departing variable. You rewrite the basis z x1 x4, x1 came in the place of a1. So, this becomes the new basis. You identify the entering variable, identify the departing variable, go to the next iteration. You see that this is how you get the new table. You get the entering variable. There is one more variable which has one variable here which has a negative value, namely x3. Therefore, you could get an entering variable. However, you want to now identify which is the departing variable. x3 wants to come in here into the basis, and therefore, one of these x1 or x2 has to go out. But when you want to see which is the departing variable, you want to calculate bi by aij for non-negative values, non-zero and non-negative values. It is not possible. So, none of these currently basic variables would like to go out now. So, there is no departing variable, which means what? The solution is not optimal here, because there is a negative coefficient sitting in the z row, and therefore, the objective function value can be further improved by bringing in this as the basic variable. However, the currently basic variables x1 and x2, neither of them can be identified as departing variable. So, which means that neither x1 nor x2 reaches 0 as you start increasing x3, and therefore, there is no departing variable that is identified, and therefore, the problem becomes unbounded. So, this is how you identify the unbounded solution. At any iteration, this is iteration 3 in this particular case, you have not yet reached the optimal solution. You have been able to identify the entering variable, but there is no departing variable that you can identify. At such situation, you just terminate the computation, say that the problem is unbounded. So, this is how you identify the unbounded solution. Let us look at the other case where we talked about infeasible solutions. Recall that in the infeasible solution or infeasible problems, you are not able to get any feasible space. So, one constraint may be looking at this direction, the other constraint may be looking at this direction. So, there is no intersecting region, and or you may have a set of constraints which define some intersecting region here and another set which define another intersecting region here, etc., but there is no common intersecting region in the feasible region, feasible quadrant here. And therefore, any time you are unable to find a feasible solution, feasible space, that problem is an infeasible problem. This you could do in the graphical case, because there are only two variables and you could see the intersection visually. However, in large problems, you must be able to identify the infeasible solution through the simplex algorithm. In the case where we introduced artificial variables, in both the problems, you just see what happened to the artificial variables. Let us say that in this particular case, you had introduced the artificial variable a1. In the next iteration, a1 was still in the basis. In the next iteration, a1 has gone out. So, a1 leaves the basis sooner than later if there is a feasible solution. The artificial variables will not sit in the basis for a long time. In fact, even if they sit in the basis for a long time, in the optimal solution, they will never figure out. They will never figure. So, in the optimal solution, you saw that a1 is 0. Similarly, in this particular case, you had put an artificial variable and then you look at the final solution. The artificial variable not exactly the final solution, because this was unbounded, but the a1 has left the basis already. So, a1 has left the basis. So, whenever you introduce the artificial variables, if the problem is feasible, the artificial variables leave the basis sooner than later. In fact, in most of the cases, if you have one or two artificial variables, within the first few iterations, the artificial variables will all leave the basis, and therefore, they become non-basic variables. Therefore, the solution in the solution, they will have artificial variables equal to 0. If the problem is infeasible, then when you reach the optimality criteria, that is that the coefficients in the z row associated with each of the variables are all non-negative. There is no negative coefficient there. If you have attained this optimality criteria, but in the basis still one or more of the artificial variables are sitting. That means what? The artificial variables have a non-zero solution. So, you have met the optimality criteria, but the artificial variables are still in the basis. Such situations will lead you to identify this as an infeasible solution. Why? It is because the artificial variables have taken a non-zero value now, and the moment an artificial variable takes a non-zero value, your objective function gets penalized, and therefore, the objective function will be pulled down much further than if you had only x1 and x2, which are the initial decision variables, if they had taken 0 value. So, z will become negative in a maximization problem, and therefore, this is a infeasible solution. So, you identify an infeasible solution by a situation in the simplex algorithm, where you have hit the optimality criteria, but the one or more artificial variables are still sitting in the basis. That is how you identify the infeasible solution. Let us look at this particular example. You are looking at minimization problem. Minimize z is equal to 3 x1 plus 5 x2, subject to x1 plus x2 less than or equal to 4 and 2 x1 plus 2 x2 greater than or equal to 32. Just look at these two constraints. One is saying x1 plus x2 less than or equal to 4, another is saying x1 plus x2 greater than or equal to 16, if you just divide it by 2 all throughout. So, this requires that x1 plus x2 be greater than or equal to 16, this requires that x1 plus x2 be less than or equal to 4, and therefore, they are conflicting with each other. They are looking at different sides of the quadrant, different sides. One is looking towards the right, another is looking towards the left, and there is no intersecting region, and obviously, this is a infeasible problem. If you plot the graph, this is how it looks. So, 2 x1 plus 2 x2 greater than or equal to 32 it is this region, and x 1 plus x 2 less than or equal to 4 is this region, and therefore, there is no intersecting region possible at all, and therefore, this is a infeasible problem. Let us solve this using our simplex algorithm to see what happens. So, you have maximize z is equal to 3 x 1 plus 5 x 2, subject to x 1 plus x 2 is less than or equal to 4. So, I will add a slack variable, make it x 1 plus x 2 plus x 3 is equal to 4. 2 x 1 plus 2 x 2 greater than or equal to 32, I will write it as 2 x 1 plus 2 x 2 minus x 4 is equal to 32. I am deducting a surplus variable, and all these are non-negative. Now, corresponding to this, now I will add a artificial variable, penalize the objective function and transform the z row using all our earlier methods. So, your z row is your z minus 3 x 1 minus 5 x 2 minus, that is plus m into a 1 is equal to 0. Then the row containing the artificial variable will be 2 x 1 plus 2 x 2 minus x 4 plus a 1 is equal to 32. So, that is a row containing the artificial variable. So, you transform like we did earlier, and this will be the transformed row, minus 3 minus 2 m minus 5 minus 2 m 0 m 0 minus 32 m. Use this transformed z row now in the first simplex W. So, this is a transformed z row, and this is your row 1 and this is row 2 in their original form, and then you solve using the using your optimality criteria. You see that minus 5 minus 2 m is higher negative value, and therefore, this becomes the entering variable, and then this becomes the departing variable, x 3 is the departing variable. So, your basis gets defined as z x 2 and a 1. So, z x 2 and a 1, and when you do the when you do the transformation, you see that all the coefficients in the z row in iteration 2 are all non-negative. Remember, m is a positive quantity and a very large number at that. So, this is also positive, and these are all non-negative, and therefore, you have reached you have satisfied the optimality criteria. That means, it says that the solution cannot be further improved. However, in the basis there is a 1 sitting here. That means, the artificial variable is taking a non-zero value, a 1 is 24 here, and the z value here is 20 minus 24 m, where m is a very large quantity, which means z is a very large negative value. So, although you have satisfied the optimality criteria here, because there is an artificial variable that is sitting in the basis, this is an infeasible solution. So, you identify the infeasible solution the moment you hit the optimality criteria, and still there is a at least one artificial variable sitting in the final tableau in the basis, that leads to an infeasible solution. So, this is how you identify infeasible solution. So, you know now how to identify multiple solutions. You identify the multiple solutions where the coefficient of one of the non-basic variables in the final tableau. By final tableau, I mean when you have met the optimality criteria, when the coefficient in the z row corresponding to one of the non-basic variables is 0. That is when you say that there are multiple solutions, and you know how to generate multiple solutions. You identify the unbounded solution where in any of the intermediate iterations, remember you have not hit the optimal solution yet in the case of unbounded solution. In any of the intermediate tableaus, you are able to identify an entering variable, but there is no corresponding departing variable, which means that the solution can be increased to infinity for a maximization problem, and therefore, that becomes unbounded solution. Then you know how to identify an infeasible solution. You have hit the optimality criteria, but one of the at least one of the artificial variables is still in the basis, and therefore, it becomes infeasible solution. So, all these special cases you know how to identify through simplex algorithm. Now, we will go to a interesting feature of the linear programming problems corresponding to any problem that we have dealt with. Let us say that you dealt with the last problem, which was infeasible. Corresponding to any problem, you can formulate a corresponding problem called as a dual problem. So, the problem that you are originally having can be termed as a primal problem, and associated with every primal problem you can formulate a dual problem. Now, the duality concept of duality is an important concept in linear programming problems. In fact, it appears to be too theoretical, because you have been able to solve the primal problem, you will be able to also solve a dual problem. There is a relationship between primal problem and a dual problem. So, a new entrant to this area will always wonder why consider duality at all. It's a very elegant theory of the linear programming problems, but a new entrant or an inexperienced user of linear programming problem will not be able to appreciate it so much, because it appears to be slightly redundant concept. But this is a very sound theory, and the old adage that there is nothing more practical than a sound theory. So, as long as the theory is sound and it is good and it is elegant in mathematical form, it is really practical. So, let us go through what we mean by a dual problem associated with a primal problem, and then later on we will see how we use the dual problems in the LP situation, in the linear programming problems. There is a concept called as sensitivity analysis. There is a topic called as sensitivity analysis in the linear programming problems. What do we mean by that? Let us say that you solved a problem. You take that z is equal to 36 problem, where you have been able to achieve a optimal solution. Let us say we are looking at this particular problem, z is equal to 36, and you got the solution x 1 is equal to 2, x 2 is equal to 6, x 3 is equal to 2, and so on. This is the optimal objective function value that you got, corresponding to the set of constraints. So, these were the sets of constraints. So, I will write here optimal z is equal to 36, and let us say this was a less than or equal to constraint, less than or equal to 18, and you saw subsequently when we solved this with the equality constraint that this solution also led to z is equal to 36. We know that this is the binding constraint. In resource allocation problems, particularly these binding constraints are important, because they represent mostly some constraints on the available resources. Let us say that we want to ask the question, this was binding, which means that this 18 has become restrictive now. What happens if I increase this right hand side value from 18 to let us say 20? What happens to my objective function? Which means we are seeking the sensitivity of the objective function to changes in the right hand side values of this the constraints. That is one type of sensitivity problem. So, in the linear programming problems, there is an important topic associated with the sensitivity of the solution. One is obtaining the optimal solution itself, but you may start asking questions on the optimal solutions. You may say, instead of right hand side being 18, if it was 16, if my resource available was much more restrictive than 18, let us say it was 16, then how much do I sacrifice on the objective function, and so on. There are several questions that you can ask. This is maximization. Therefore, let us say that instead of 3 it was 2, what happens to my objective function? All such questions you can answer using the final optimal solution itself. You got the optimal solution, let us say that I have changed it to 16. You do not have to resolve the problem by reintroducing this constraint. From the optimal solution itself, you should be able to answer questions on sensitivity of the solution to various small changes that you make, either on the right hand side of the objective constraints or on the coefficients in the objective function, or on the coefficients of the constraint set itself, and so on. So, you will be able to answer questions such as how sensitive is my objective function, optimal objective function value or the optimal solution to small changes that can happen on the right hand side of the constraints, on the coefficients of the constraints, or on the coefficients of the objective function, and so on. The concept of duality that we are going to introduce now is closely associated with the sensitivity analysis. Although you can still do the sensitivity analysis without understanding the concept of duality. So, duality is a strong theoretical aspect of the linear programming, and it can also be used for in many practical situations. We will introduce the concept of duality in the and how we formulate the dual problems associated with a primal problem. This we will do in the next lecture. So, essentially in today's lecture, we started off with the multiple solutions, identification of multiple solutions, which was covered in the last lecture, and then we went on to identify unbounded solutions, and then we also examined a problem of unbounded problem related to unbounded solution. Recall that unbounded solution you can identify when there is no departing variable at any iteration. Then you identified an infeasible solution. An infeasible solution you identify when you meet the optimality criteria in the simplex algorithm, but there is a artificial variable setting. And we have also seen how you introduce the artificial variables in the case of equality constraints and greater than or equal to constraints. And remember always that you introduce the artificial variables just to make sure that you get an initial basic feasible solution to start off the computations, and the artificial variables should sooner than later leave the basis. If they do not leave the basis, even when the optimality criteria is met, it indicates that the problem is infeasible. So, in the next lecture, we will introduce the concept of duality and see how we formulate a dual problem associated with any given linear programming problem. Thank you for your attention. We will continue the discussion.